Hello and welcome to my YouTube channel. My name is Aaron, and in this video series we're going to be analyzing systems of gears. They're often called geared trains, gearboxes, or transmissions. In order to analyze these, we need to understand the concept of rolling contacts. So we have a gear here we'll call X and a gear we will call Y. And X has a radius we will call rho X. We'll use the Greek letter rho. Y for the radius of Y. And they touch each other at a point here, a point on X and a point on Y that are coincident. We will call this point PXY. And the point on X and the point on Y move at the exact same linear velocity. We will call that VPXY. And let's say that gear X is rotating that direction. We'll say it's rotating with speed omega X. We use omega for angular velocity in RPM, rotations per minute. And we use a V for linear velocity. And so if gear X is rotating this direction and the point P is moving in this direction, if we were to trace this point on X over some amount of time, it would trace out an arc like this. The same thing if we were to trace the point on Y for the same amount of time, it would trace out an arc like this. And so if they're moving at the same velocity, the same linear velocity, and for the same amount of time, then we know that this arc length here, S, is the same, it's equal to this arc length here on X. So now let's look at how the angular velocity of X is related to the angular velocity of Y through the rolling contact. So we're going to go ahead and hide this, and let's just put back our labels. Call this X and Y. This had a radius of rho X and a radius of rho Y. And we're going to go ahead and now introduce a new vector extending from the center of X down to the center of Y. This vector is called the arm. And it's stationary in a simple gear train. The definition of a simple gear train has a stationary arm, but we will use that to reference the other vectors that we're about to add. We're going to add a vector to X. We'll call that vector Rx, and we will add a vector to Y, and we'll call that vector Ry with the bar over it. And we measure this angle theta Y, and this angle theta X, referenced from the arm. We said that X had an angular velocity of omega X, so let's just say that the vector Rx had an initial position here and Ry had an initial position here. So as Ry rotates along here and Rx rotates, we know that these two arc lengths are going to be equal to each other. So we can relate theta X and theta Y through the following equation. Rho X times the change in theta X relative to the arm is equal to rho Y times the change in theta Y relative to the arm. Now in this case the arm is stationary, so that relative motion to the arm is not going to be significant, but in cases of like a planetary gearbox, the arm is not stationary, so it's important that we look at the change in velocity relative to the arm. So while theta X is rotating counterclockwise, we have theta Y rotates clockwise. We consider counterclockwise to be positive and clockwise to be negative, so we're actually going to need a negative sign here on the right hand side of the equation, and this is the equation for a pair of gears rolling externally. So it is the external rolling contact equation. Rolling contact equation. So let's just expand this out. Rho x times delta theta x relative to the arm, so minus delta theta arm, is equal to minus rho y times delta theta y relative to the arm, delta theta arm. Okay, and like we said, there is no, the arm is stationary, so there's no change in the arm position, so this will just be 0 and 0. So we can expand this into rho x times delta theta x is just theta x minus the initial value of theta x, so we'll say theta xi, which is just this angle right here, which is equal to minus rho y times theta y minus the initial value of y, theta y I, which was just this angle here. And let's just take a second to see what this equation is telling us. Basically, theta x depends on the value of the initial position of theta x as well as the position of, or the value of, theta y. And in most applications for gearboxes and transmissions, we don't really care about the positions of gears. Maybe if we had a robotics application with a robotic arm attached to the gear, then we might be interested in the position of that arm. But for transmissions and gearboxes, we're usually only interested in the velocity of gears and how they relate to each other. So to get this equation in terms of their velocities, what we're going to do is we're going to differentiate with respect to time. Differentiating with respect to time gives us rho x times the derivative of theta x with respect to time. That's a position, so the derivative would be the velocity, omega x, minus the value of theta xi is a constant, so the derivative of a constant would be 0, is equal to minus rho y times, again, theta y would be the derivative would be omega y, the velocity of y, minus, again, theta y I is a constant, so that would also be 0. And this simplifies down to rho x times omega x is equal to minus rho y times omega y. The definition of a gear ratio R is equal to the input omega in over omega out. So the input speed over the output speed. So let's say that gear X is the input and gear Y is the output, and it's got some angular speed omega y. Then solving this equation for the gear ratio would give us omega x over omega y is equal to minus rho y over rho x. And if we know the number of gear teeth on x, we'll call that nx, and the number of gear teeth on y, we'll call that ny. Oftentimes we'll just write this equation in terms of the gear teeth because that the number of teeth is proportional to the radius of the gear. So we can say ny over nx. That's it. So if we know the input speed of omega x, we can calculate the output speed omega y by omega out is equal to omega in divided by r. And we said that r is negative ny over nx. So that's how the input speed relates to the output speed using the gear ratio. So now let's look at the input torque and how that relates to the output torque using the gear ratio. Now I'll erase this and let's look at how the torque, the input torque, relates to the output torque using the gear ratio. We know that power is equal to the torque times the angular velocity, omega. So what we'll say is that the power going into the system is the same as the power going out of the system, assuming there's no losses. So we know that the torque on x times the speed of x, omega x, is equal to the torque on y times the speed of y. So now we can write this as the torque on x times omega x divided by omega y. Omega x is the input, omega y is the output, is equal to the torque on y. Now we can rearrange this to be the torque on y is equal to omega x over omega y is just the gear ratio r times the torque on x. To summarize, I'll put the speed equation back up, which we said the output speed omega y was equal to the input speed omega x over the gear ratio r, which from the rolling contact equation we found r was equal to minus rho y, the radius of y, over rho x, which can be written as minus ny, the number of gear teeth on y, over nx, the number of gear teeth on x. So once we have the gear ratio, we can use this relationship between torque and speed for any gearbox. And I know it seems a bit cumbersome to go through the rolling contact equations to find a simple gear ratio, but in the next video, when we do a slightly more complicated gear system with compound gears, and then eventually we'll do planetary gear systems, it becomes quite clear how the rolling contact equations really simplifies the process of calculating the gear ratio. If you like this video, please give it a thumbs up, subscribe if you want more, leave your questions and comments down below, and thanks for watching.